everyone. Welcome to the webinar. We're just going to give another minute or two for more people to join in, but thank you guys all for signing on. Okay, good afternoon, everyone. My name is Sedona Ryan. I'm the research coordinator here for UNCIE and the CMAS Center. And we're so happy that all of you are able to join us here today for our webinar series with today's speaker, Dr. Patrick Campbell, who's going to be presenting to us on NOAA's global forecast system data in the cloud for community air quality modeling. So next slide, please. Just to run through a quick series of tools that we have for you as attendees to keep things a little bit more orderly. Attendees are not able to speak directly, but we do have a number of ways in which you can voice questions, comments, things like that throughout the presentation to be answered at the end or by panelists throughout. So first, if there are any technical issues or Zoom issues that you need to connect with us about, you can use the chat feature. But then we also have a designated Q&A feature there at the bottom of your screen for any actual content or technical questions for our speaker, Patrick, or any of the other panelists. So please don't hesitate to ask questions, and we will answer all of these at the end. And finally, we have a poll feature. We would really greatly appreciate you guys to participate in these. We're actually going to do a little introductory poll now to test that out. And so that should pop up on your screen in a moment, and we would encourage all of you to participate. So here are just a few questions. We'd love to hear from you guys. Just give one more minute here. All right, well, thank you all for your feedback there. We'll have one more poll at the end, so stay tuned for that. And now I'd like to introduce Dr. Aruna Chalam, who will be more formally introducing our speaker for today. So thank you all.
Thank you, Sarona. Good afternoon to all attendees from the CMAS community. Thanks for joining this afternoon's session, the webinar to be given by Dr. Patrick Campbell. It's my pleasure to introduce Dr. Patrick Campbell. Dr. Campbell completed his PhD in atmospheric sciences in 2013 from the University of Wyoming. Currently, he is a research associate professor at George Mason University's Center for Spatial Information Science and Systems, and is the associate director of GMU's Satellite and Earth System Studies program. Dr. Campbell is an affiliate of NOAA's Air Resources Laboratory under the Cooperative Institute for Satellite Earth System Studies, where he is working closely with the ARL team on research and development of the next generation weather and atmospheric composition models that help protect human ecosystem health across scales. With that, Patrick, it's all yours.
Thank you, Saurav. And thank you so much to the CMAS Center for allowing me to give this webinar to the community. And I'm really here on behalf of all my colleagues at George Mason University and NOAA Air Resources Laboratory. And I also acknowledge this is completed through the Cooperative Institute for Satellite Earth System Studies, or CISIS, allows us to work on research between George Mason University and NOAA. So yes, I'm pleased to be here, and thank you everybody for joining. And I'm here to present today on the use of NOAA's Global Forecast System data in the cloud for community air quality modeling. And I hope that these cloud tools that I present today is useful to the CMAS community, both now and in the future, hopefully. And so I just want to present initially here a brief outline of what I'll be talking about today. There'll be really 5 parts. First is the background on NOAA's GFS, or Global Forecast System model, and the NAC. I'll explain that in a moment, what NAC is. And then I will be discussing about the Amazon Web Services cloud HPC environments and the software NAC in the cloud. And then I'll discuss some about the development of NAC Cloud's interface, the web-based interface used for the community. And then I'll provide a few brief examples of current applications of NAC Cloud, and then just some conclusions and final notes, and hopefully a path forward for NAC Cloud in the community. So we'll start with some background. And here I summarize NOAA's Global Forecast System, or GFS. I'm sure many of you have heard of the GFS and its usage for the National Weather Service's weather forecasts that we receive daily and impact our daily lives. And at NOAA's Environmental Modeling Center, it is the operational GFS version 16 currently. And this version uses what is known as a finite volume cube sphere, or FV3 dynamical core. And it has a pretty extensive vertical structure of up to 127 layers that extends up quite high, up to about 80 kilometers in the atmosphere. The first model layer thickness is relatively refined at 20 meters, capture boundary layer processes. And it has a relatively high spatial resolution for global models for the state of the science at approximately 13 kilometers horizontal spatial resolution. I will say it has been quite advanced for its physical parameterizations. It uses a novel global data assimilation system, or GDAS. Important to our work here, it also includes CF compliant NetCDF forecast history files as output. And we'll get into why that's important for us in this work here. And it provides hourly output out to a 3-day or 72-hour forecast. And currently, it's used in the current operational, or it was just a previous operational air quality forecast system at NOAA. The physics itself are still used in the air quality forecast system operationally from GFS. So this is very pertinent information to air quality modeling, as I'll discuss for NAC Cloud. And if you want to see some more information on how it's coupled, how it can be coupled to state of the science model, air quality models like CMAC, or the Community Multi-Scale Air Quality Model, you can see our GMD paper in 2022. So here I will describe what is known as the NOAA EPA Atmospheric Chemistry Coupler, or NAC. And I call it that because it really is an acquired skill And we've adapted this from EPA tools, including the EPA's Meteorology Chemistry Interface Processor, or MSIP version 5. And I'm not sure how many are familiar with MSIP, but I'm sure some of you are, and it's a widely known tool that's used to couple WRF to the Community Multiscale Air Quality Model, again, or CMAC. Here, though, we've adapted this tool and restructured MSIP to be used for global FE3 GFS data from NOAA. And here, what we do is, if we look in the middle panel, we can interpolate these horizontal fields directly, such as surface temperature shown here. And we also have options on the far right side to use either the native three-dimensional vertical structure or redefine it. And that basically allows us to use the native vertical resolution from GFS of 127 layers. That's a lot of layers. So we also brought back the capability for NAC to sort of native, or to take these native levels and collapse them or interpolate them to a coarser resolution, more suitable or applicable to air quality modeling. And that just, well, I will note that there is a good agreement in structure when we compare the native vertical levels versus the interpolated vertical levels in NAC. On the far left, I just show a schematic of what really NAC is. It's pretty brief and high level, but I will say important to the work in NAC is that we've introduced the MPI parallelization into NAC to optimize the processing speeds, because the GFS data is very large, it's global, relatively high resolution, so the use of MPI is very important for that. And NAC is available to the greater scientific community at the GitHub page shown below, and we have numerous publications describing what it is, its evaluation, and applications. So that's some about the background of NOAA's GFS version 16 and the NAC tool. But now we're going to transition to talk about the AWS, or Amazon Web Services cloud platform, and using NAC in the cloud. But first, we should ask the question, why bring NOAA's GFS version 16 data and NAC into the cloud? Well, to start, obtaining a lot of this large data and these processing tools and running the gridded meteorological models like WRF, or downscale WRF for CMAC applications across the globe can be very time and resource intensive. And not everybody can do it. And I will say, setting up these downscaled, as I from experience know, setting up these downscaled WRF simulations for people that are not necessarily experts in meteorology can be prone to error and maybe poor physics choices. I will say there can be inherent inconsistencies between what is used for the driving large-scale meteorology initial and boundary conditions that are downscaled to WRF. There can be inherent inconsistencies across physics. Also, in the second bullet, I will say that the NOAA's operational GFS 16, again, this is global, relatively high resolution in NetCDF format, and hourly as we need it for CMAC. While it's robust, it really can be pretty large data sets and cumbersome to process for the community. It's really data I/O. It's intensive, and so we chose to go the route of the cloud because cloud computing and storage platforms are pretty desirable. They're very customizable. In this case, very important to this case, that they can be on demand. And I'll show they can be pretty scalable for your applications than traditional local servers. And in this case, I like to bold and put this emphasis on this, is that we can use the cloud to produce user-ready CMAC inputs, such as the MET conditions here. So the main objective in this project, at the start of this project, is to develop this cloud application and interface to NOAA's GFS-driven CMAC applications that can be used for the community for any regional domain globally. And we call this platform NAC Cloud. So how do we do this? Well, some of the methods I'll show here very simply, and I'll step through the schematic shown here. And on the left side, in blue, I'll just simply say that there's a daily cloud transfer from the NOAA NCEP servers where GFS is run operationally every day, 4 times a day. It directly transfers from the NOAA servers to the cloud every day at about 1800 UTC. And then we just simply store this very large, though, gridded hourly NetCDF GFS data on the cloud. And I'll get into how we do that in a moment. But then more importantly, maybe on the right-hand side to the user, we have created in the yellow box here, shown in the yellow box, an on-demand HPC built in the Amazon Web Services cloud platform that is driven by a simple web application that I'll show later. Excuse me. This allows the user to enter all the necessary details on really what time they want to run, what domain they want to run to process this global GFS data for CMAC applications. And so what happens is it'll initiate on demand the NAT Cloud software in the gray box below the yellow one to run and process this data to provide the user CMAC model ready output for any domain. And then that can be used to drive community air quality models like CMAC. And so I'll have some pretty busy diagrams here on the left and a table, but it really describes the overall Amazon Web Services based development and the HPC configurations that we use in this project. So in the figure on the top left up here, we'll start on the left, and this is where we initiate that transfer and that storage of the GFS data from the NCEP NOAA servers to the what is known as the Simple Storage Solution, or S3 buckets on Amazon Web Services. Here we chose to use the Glacier Instant Retrieval, or the Glacier IR, if you're familiar with AWS. And that interchanges and interfaces with a standard S3 bucket. And what that does is it passes data on demand from a longer term storage on the S3 standard bucket to the instant Glacier retrieval, such that we can pull data from that very quickly. It's not a slow process like a long-term archive would be on a normal server. And then the HPC cluster on the right here is created. We created this based on Amazon Web Services Parallel Cluster. This is a cluster management tool that's built on open source tools such as CFN Cluster project for AWS. And the AWS Parallel Cluster uses either text files or, in this case, a graphical user interface. It's to really customize and configure, all the resources needed for one's HPC applications in a very automated way. And in this case, we run this configuration with Slurm as the job scheduler to run NAT Cloud V1. And we have major elements here shown in the table below for this cluster. Some of the important things are to note that we use, again, the scheduler, a Slurm scheduler. We use a certain capacity type, which is on demand, which is very useful to only initiate and run the HPC cluster on demand, as it's not operational. It's more research-based. And we also use what's known as the Amazon FSx for Lustre system storage type, which allows us to easily move the data from S3 storage to the cluster-based file management system that can be ready for NAC, the NAC Cloud software on demand. And then we have also tested within this configuration the scalability of NAC Cloud. As I mentioned, NAC Cloud has MPI-based parallel codes. So we do a very simple time splitting to optimize the runs, where each time or hour runs as a separate MPI task. So we run a series of experiments shown here for the maximum memory atop versus domain size for the user chosen domain size on the top, and on the bottom is runtime versus domain size. And I'll just jump into the results that, if you look at this line here, we see that the maximum job memory required scales very linearly with the domain size chosen for NAT Cloud. And we use this linear line to simply estimate the memory needs for any given Slurm job within this HPC cloud platform to request the number of resources accordingly. We don't want to overspend, as cloud can be costly for an HPC resource. And then the below is not quite as linear. This is the runtime for NAT Cloud versus domain size, but it's nearly linear with some variability due to spinning up an on-demand cluster each time a job is initiated. That can introduce some variability, but I will say that it's roughly linear and that these results suggest that NAC is pretty scalable in the cloud platform. So that's a bit about the HPC environment and on Amazon Cloud. and NAC, but here we're going to get a little bit more into the details of the development of the useful, hopefully the useful NAC Cloud interface for the community to use this tool. And so here we'll talk about the development of this web-based user interface, and it really is consists of 4 main components, excuse me, for development. And I'll start in the first bullet. So what we use is a web application known as the NOAA ARL's Ready framework. You may not know much about that's the Ready framework using Java ecosystem, but you may be familiar with the high split model at ARL, and that is also used as this Ready framework for the web application when you initiate your trajectory runs, maybe using the ARL's high split model. But Ready stands for Real-Time Environmental Applications and Display System, and that is what we use to initiate the web front for NAC Cloud. And then in the second bullet, we use a simple NAC Fortran nameless generation and job scripts using Python that are initiated by the web application form input. And I'll show that next, how that form is communicated. And then that is communicated via an API endpoint through the web app. And then we use, again, I'll kind of reemphasize, we use Slurm job submission, but we use the Slurm REST API using Python client libraries to submit the jobs through the web form. And it's very useful. The REST APIs are very flexible, lightweight ways to integrate these web applications to behave in a certain expected way for these developments. And then we simply have a job that syncs after NAC Cloud runs. It generates the outputs from the Amazon FSx for Lustra. That's the cluster-based file management. It moves all the data to the Amazon S3 bucket where they can be picked up and downloaded directly from the user. And this is by using the URLs right now, where the user can download those. And so I'd like to just do a quick demo if I have time. I think we're moving through pretty quickly, so I should have time to step through what this web front looks like, and then maybe a very, very quick demo of just seeing it in motion. So what I'm showing here is simply the web front page that you would see if you logged in. Well, you've requested access and you've logged in, you've gotten access and logged into the web front. And what we see here are some simple box commands. And I'll just step through some of what these inputs are. And some of these should be quite familiar to you if you've used the CMAC model for your air quality modeling applications. So the first thing you would enter, of course, is the start and end dates for your requested simulation time. And then you have a starting hour and an ending hour. Here, the 12Z is fixed because the GFS output that we use in this case is only from a single cycle starting at 12Z, but the ending hour can be flexible. So you need to have your starting and end date and time conditions. And then we have the grid type. So NAC Cloud supports 2 grid types. Of course, we support mainly this regional domain, the Lambert conic conformal projection for CMAC applications. But this also can be changed to polar stereographic projection for things like hemispheric CMAC applications. And then we have the P alpha, P beta terms, and these are pertain to, of course, the true latitudes for your cone for Lambert conformal case, and the P gamma is the central meridian of your projection. We have the X cent and Y cent. These are your reference longitude and latitudes for your domain. And then if you're familiar with CMAC, these X origin and Y origins, these are your X and Y coordinates from the grid origin, the lower left corner of your domain. And this is in meters here. And then we have the X cell and the Y cell, of course. These are your dimensions, your grid resolution. Here I just show a typical example of a 12 kilometer or 12,000 meter resolution. And then you have the number of grids, of course, the eventual size of your domain, the n columns and n rows. We also, as I mentioned before, this ability to use the native vertical resolution of GFS, the 127 layers, or you can compress and interpolate them down to something that might be more manageable for your application. And here's where you can do that in the CTM lays option. And you can enter here the sigma levels for redefining the vertical structure of GFS. Here I just show a typical configuration for a 35-layer air quality forecast model at NOAA, but you can enter whatever configuration you desire, or enter just -1, and that would give you the native resolution at 127 layers. So what I'm going to do now is I'm going to try to click on, turn off my laser pointer. I'm going to click on the link so you can see what happens here. I need to slide a window over. But if you, here's where you would click to register to get your login credentials, and we would work with you to provide those. But after you would have that, you would click on Start Preparation Run, and then you have your login credentials. I'm simply logging in as myself. We have all the default configurations for a CONUS domain, as I just described, for 35 CONUS regional domain and a 35-layer vertical configuration. And so that would be just what I'm going to show here, but you can change any of these to suit your domain anywhere across the world. And then you simply click Start. And what you'll see if you're familiar maybe with the high split models, you're going to see a sort of a window box here, sort of refreshing as the model runs. In this case, it'll only refresh really once in the current NAT Cloud configuration. And what you'll see is a whole bunch of job information above, maybe kind of cryptic. We can try to improve this in the future, but most importantly right now is here are the, after NAT Cloud runs, here are your S3 bucket URLs for the outputs to pick up. And these should be familiar to you if you use CMAC. These have your grid information, your grid boundary, and your grid cross information, and your grid dot information. It has land use data, also has the meteorology, 3D and two-dimensional meteorology conditions and soil conditions, and your grid description file, of course. These can all be picked up using a simple wget commands, or you can enter all this information, copy and paste this into like a text file and use things like wget -i in that file to download them. And if the job is finished, you should wait probably 30 minutes to make sure that it finishes. But depending on the length of your simulation, you can download all those files immediately for your CMAC application. So if I can close this and get back to the presentation, that's just a very brief demo. And then after that runs successfully, this is something you would see as your output. This is plotted using just a simple Python or NCL, but you'll have all the output to analyze prior to your CMAX simulation. And what I show here is just a comparison of the GFS version 16 inputs on the top row versus the NAT Cloud output on the bottom row. And this is for surface temperature, 10-meter wind speed, and the PBL height. And really all I wanted to demonstrate here is that it really, using NAT Cloud, it results in excellent agreement, spatial agreement between the GFS inputs and the NAT Cloud outputs. And further evaluation of this same data set here, simply showing just a regression analysis of all the points in this CONUS domain I just showed previously. Here we have the NAT Cloud on the y-axis and the GFS 16 inputs on the x-axis. And what we see is there's nearly a linear one-to-one relationship with R-squared values, as we expect, really close to 1. And it provides more confidence in using this NAT Cloud system for user GFS-driven CMAC applications anywhere regionally across the globe. And so that's some of the development of this NAT Cloud interface and for the community and something about the outputs. Now I'll go into some brief examples of current applications of NAT Cloud. And I will say that NAT Cloud, there are numerous NAT Cloud users. They span across different US states and countries across the world, where I just list a few examples here to highlight. And at the federal level, there's a project known as the Quasi Real-Time Modeling Project. This is an effort at the EPA, Office of Air Quality and Planning and Standards, I think OAQPS, to use the more near real-time NAT Cloud outputs, the meta outputs, for more of a rapid response, multi-configuration ensemble option to drive CMAX simulations. And in this case, the NAT Cloud can be useful, and it can help be more drive more quickly CMAX simulations to identify model performance issues or features that can lead to faster improvement, and really just enhance more quickly the ability to do different scientific assessments at the EPA using NOAA operational GFS data for the meteorology conditions. Another exciting project I'd like to highlight is this EMBER project from the US EPA in the second bullet. And the EMBER project is known as Expedited Modeling of Burn Events Results. And NAT Cloud is being used there as their meteorological data inputs, which again really allows for this more near real-time application of CMAC for impacts of things like fires, wildfires on ozone or PM 2.5, particulate matter. Really, this helps an agency who has not really been able to, in the past, been able to perform maybe such rapid CMAC scientific assessments for more near real-time events, like extreme events, like wildfires in this case. So I'm really excited about the use of NAT Cloud in that project. And another example of NAT Cloud to highlight is at the state level. So the Georgia Environmental Protection Division is one example, and they issue their air quality forecasting daily, as many state agencies do across the country, and using maybe even things like the operational air quality forecast from NOAA. But they sometimes run their own air quality forecast models, their own photochemical transport models. And so as part of their efforts, their forecasting efforts, they want to use multiple different sources of meteorology inputs to predict things like the concentrations of air pollutants with different photochemical air quality transport models. So here the Georgia EPD has completed some test NAT Cloud runs, and they want to use NAT Cloud to prepare the necessary initial and boundary conditions for their own photochemical modeling system runs for air quality forecasting in their region. So you can see more of maybe a national, federal level applications of NAT Cloud, but also state level, more local air quality forecasting applications such as that. So just wanted to highlight some of the examples of what NAT Cloud could be used for, is being used for, and also could be used for in the future. And so I'd like to just actually now move into some of the conclusions and path forward. So I'd like to just note that NAT Cloud has been developed and does have a functional web-based interface for the community. You can find that at the NAC webpage shown here, and also we have a paper describing more details of NAT Cloud if you're interested, and potential applications of NAT Cloud. And so NAT Cloud is available for your GFS-driven CMAC applications for any regional domain you desire. And it's available for the entire operational GFS version 16 data record. That starts in March of 2021 and goes through the current day. And as I mentioned, this is updated daily at about 18 UTC every day. And just please, yes, so contact me for any further questions or collaboration ideas for using NAT Cloud for your applications. And I wanted to leave with also some final notes about the cloud in this application. Unfortunately, we are needing to explore for some additional funding sources to continue NAT Cloud on AWS, as NAT Cloud has starting to reach or extended past its lifetime. It initially started as a one-year project at NOAA in 2022, and we're actively pursuing other funding opportunities to continue NAT Cloud. And we want to maintain this continuous near real-time GFS MET record on the cloud and the on-demand HPC, which includes the NAT Cloud tool for the community. As we're seeing, it's very useful, but we need to like to continue that and not have a break in the record. So please let me know if you're interested in getting involved or other ways that we can continue NAT Cloud for your application. And in the second bullet, I will note that, yes, we know that using cloud storage and HPC resources can be quite costly upfront. and costly to maintain, depending on the application. But I will say in the third bullet, sort of in contrast to this, the overall cost of something like the cloud application of NAT Cloud can be much less expensive than the overall costs to maintain dedicated on-site HPC servers, and with the necessary support, person support to run research or operational grade numerical weather prediction models like WRF, which is again really why we wanted to start this application, NAT Cloud, for the community. And I will also say, lastly, again, in sort of harmony with that, the cloud resources are also very available, very widely available. They're relatively easy to set up. They can be on demand. And again, that's something very useful for NAT Cloud. We run the HPC simply on demand when a user wants to. It doesn't run operationally and continue to incur costs. It just runs when the user would like to process GFS for CMAC applications. And again, very scalable, as we showed. And so with a dedicated funding source, the cloud can become very advantageous and stable for your applications, as I think we've shown here for NAT Cloud, and hope to continue that in the future. So where can you access NAT Cloud? Well, here I have the links, which you should have available to you in the presentation online available eventually, but also the QR codes if you want to get a snapshot of where to access NAT Cloud, and also where to request to get your credentials, as we need to give you credentials to access. And then also we'd like to get your feedback, so that we can help use it for our own understanding, of the interest from the community and the users of NAT Cloud for their applications that can help garner our available funding in the future. And on that note, we do have, I think, a pretty brief online poll that we could initiate right now and get your feedback about NAT Cloud in this presentation. So thank you, everybody, for listening, and take any questions.
It looks like we have one question so far in the Q&A. We'll give people a few minutes to type those in, but if anyone else has the same question about getting a copy of the slides, we'll be posting both a recording of the webinar and the slides on our CMAS website within the next day or two, so you will be able to access these as well, in addition to these QR codes that are on the screen now to get into the NAT Cloud website and Google form.
I just wanted to ask a question since I'm on the panel. We get a lot of requests for the CMAC training for, like when we do training in Brazil, for instance, to do something in their region. So I kind of feel like this would be the perfect opportunity to use NAT Cloud to set up the initial and boundary conditions and then run for a specific region for educational purposes and also to show the power of using the parallel cluster to both do this pre-processing of the meteorology and also to run CMAC. So it'd be a really nice.
Yeah, that's what I was hoping, Liz, is that we could somehow team up to include it. I know we'd never continue the conversation after CMAS, but yeah, after the conference. But we should do. I think we should do that. Yeah, if that's an opportunity for NatCloud to be useful. Yeah. Yeah, that's, I think, part of the power is we can, I was hoping part of the power was to choose any domain, not just, CMAC is very widely used over the US and is also very widely used globally. Yes, but I think it's even harder sometimes in other parts of the world with available resources or capability to run downscale WRF simulations for CMAC. And if it can be used for educational purposes, yes, I'd love to be involved in a conversation. Yeah.
Patrick, I have a question based upon your presentation, and that's on the emissions. You did not talk about emissions, so could you talk about how people could bring in emissions inventories into the NatCloud for their custom domain?
That's a great question, Saurabh. We don't do emissions in NAC. It's only for the meteorology, similar to how MSIP was used in WRF to downscale just the WRF meteorology for CMAC. The emissions, we have not done that. I don't know what efforts there are in other tools like Smoke, right? The Smoke platform in the cloud. Maybe Liz can speak for more of that, but I think for the CMAC simulations and the critical emissions that you bring up would be very useful to have something in the cloud to provide that critical input. Yeah, it is arguably the most important input for any air quality model application. And to have that cloud capability would be very useful. And at least have the data there, right, for CMAC applications. But maybe Liz could speak more on that. Unfortunately, we don't do that in NAC. It's just for the meteorology.
Okay, thanks. Yeah, that's a significant part, and I was trying to understand with NatCloud how that may work for the community.
Right. Yes. I know that for CMAC in the cloud, Liz, right, it has the emissions are a data set that is included, right, in the cloud for CMAC applications, right?
Right. So we provide, well, we've uploaded data for, I guess, emission inventories, and also the equates inputs are available on S3 buckets. And so if you're just wanting to do something in the US area, then that would be fairly easy. But I think for training purposes where we run Smoke for like a small region outside of the US, if we could get that capability set up and then demonstrate NAC as a tie-in for generating the meteorology, just being able to enable other folks to show that if they've developed the emission inventories for their area and can get them pre-processed for CMAC, that this would be the next step to make it easier.
Yeah, I agree with you. I kind of want to add to that and say that the reason why we didn't, we were considering trying to bring our whole operational sort of air quality forecast model and all the inputs that we use for the national air quality forecasting capability, or NAQFC at NOAA, to the cloud. But that's a little bit outside of our reach. And so that's why when NAC was used for the operational system, up until this past May, it was used as the operational MET driver offline for offline CMAC. We have since gone online, and so it's not using operational anymore. I thought that, for emissions, it's very tailored to a specific application. I think emissions are something that, for any given region or any given experiment, scientifically, would be really something a user would come with for their CMAC application, which is why I thought the meteorology, not to downplay it at all in any way, or it's how critical it is to know how to set up a WRF simulation, a MET simulation, and understand the MET driving conditions into any air quality simulation. But the MET can be, I think, sort of something that's a little more generalized compared to emissions. of course, there can be many different meteorological sensitivities you could do, and people do that all the time in their applications. I kind of wanted this tool to take that piece out for some that don't have the capability or the resources to run a MET simulation, but would probably still come with their own emissions. But that is a fair point. That I think that it's just as important or more as the MET for any air quality simulation. Something to consider. Yes.
And following up on that, Patrick, how about initial boundary conditions? Do you have any setup for the custom domain? You showed how we can customize the domain based upon users' interests. So for
Right.
that domain, the current protocol, I guess I'm hearing, is the user brings their own emissions for that. But do you also have any support for creating initial boundary conditions for that application?
Yes. For chemical or
Yes,
meteorology?
for chemical.
For chemical,
Chemical,
no.
yeah.
Yeah, that's a good point. No, we don't. Yeah, it just generates the MET ICBCs really here from NAT Cloud. Yeah, and then another critical input you highlight, Saurav, is the chemical ICBCs, right? And that NAC does not handle that either. That is something else that a user would have to do another way offline.
Okay.
Yeah.
Yeah, I still think this is very powerful. You have a domain, which is something that can be customized for users' demands, and they create the metrology. But there needs to be additional work outside the NAC cloud to create the other set of inputs that CMAC needs before you come back and run CMAC.
Yeah, and you bring up something I would really love to do with future work, and continued funding and support of this can turn into something like that. We could, because we do work at NOAA and GMU in emissions development and modeling at different scales. So potentially something along the lines of a global emission inventory that had enough species, right? It also depends on your chemical mechanism. It's very specific to any given CMAC application, which is why I kind of avoided it with NAT Cloud at first, to handle the meteorology from NOAA, as we do really strong meteorology modeling there. But all those tools could be made available in some way, and starting from like a global emission inventory and being able to select your domain and species of interest could be a similar on-demand type of application as NAT Cloud, or brought into NAT Cloud and be another part of it. But that would certainly require different options and different ideas of what you'd want for emissions or ICBCs, chemical ICBCs.
Right. And you touched upon it earlier a little bit in terms of what the CMAS Center has in terms of smoke emissions processing. We don't have smoke on the cloud yet, but the plan is to have smoke on the cloud too. We'll provide the emissions inventories that the EPA puts out typically for the national emissions inventories, the NEI, but it'll be US specific. But we could explore options, I guess, down the road to see how we can perhaps have global emissions inventories and then have small scripts that can be adapted to, create CMAC ready emissions. And potentially there's a link we can make to what NAC Cloud does for the metrology and put them all together.
I think the platform itself, we could help cross-pollinate. The developments we've done here are very transferable to something like that, right? The environment, so you need to set up the AWS environment, the HPC, these web interfaces through the cloud, and using typical programming tools like Python and Java, all could be transferable to another application, which is a part of the hope. If we focus on the NAC and the meteorology, another group can help pick this up and focus on doing something similar for global emissions and regional domain specific things to pull it for the user, and maybe same thing for chemical ICBCs from a global forecast model like GOCF or something. They do a global chemical forecast of full chemistry, so that could be useful for CMAC. But the tools themselves, I think, are the power here too. Is they can be picked up if we cross-pollinate and collaborate, picked up and moved to another application like emissions or ICBCs. Yes.
Yeah,
that'd be really exciting. Really exciting.
Yeah, I think we pick up another conversation to follow up on this, and there are some great ideas here. Thank you. Sarona, do we have any other questions from the community?
Nope, I think that was all of them. If you are interested in a certification for this, you can reach out to me via email. I put my address there.
Thanks.
Okay. With that, I think we could wrap up. Let me take a moment to thank our speaker, Patrick Campbell, for a very nice presentation and present this capability. As people on the webinar know, the CMAS Center has been pushing the bounds of cloud computing with testing the CMAC model on multiple environments, and a lot of guidance has been put out in the last couple of years. So on that note, the presentation today from Dr. Campbell was very much complimentary in terms of what NOAA and his team has been up to with the NAC cloud. It's nice to hear these capabilities. Let's give a round of applause to Dr. Patrick Campbell for a very nice presentation today. And I'll turn it over to Sarona to wrap up.
Great, thank you.
Let me move the slide over for you. Okay.
Yes, thank you, Saurav, and thank you, Patrick. So just one more reminder that the CMAS conference is coming up this October from the 21st to the 23rd in Chapel Hill. And so if you're interested in submitting an abstract for that, the deadline is July 1st. All of the information about that is on our website at cmascenter.org. And if you want to jump to the next slide as well. We have all of the different session topics that you could submit your abstract for. And in particular, we want to highlight that we do have a cloud computing session. So if you have something similar or related to this that you'd like to submit an abstract for, we do really encourage that, especially in the cloud computing session. And another thing, if anyone has their own kind of webinar topic, something they'd be interested in presenting to the CMAS community that you think would be of use, you can reach out to any of us and we would love to make that happen as well. So thank you all so much. And feel free to send any last questions in the chat or Q&A as needed. Thank you, guys.
Yeah, we can stay on for a couple of minutes. If somebody has another question, they want to chat directly, we can unmute them as needed and chat. Oh, beyond Kim.
I can allow him to.
Yeah.
Should be able to speak.
Hey,
I see that
Beyond,
he's still,
you able to
still
speak now?
muted.
Can you hear me now?
Yes.
All right. I put something on the chat box and I wasn't sure whether that was visible to you guys. So just want to make sure because that was a clarification comment.
Yes, I saw that. Appreciate the clarification. Right. Yeah. So it's really exploratory, right? Right now using that cloud.
Yeah, it's a very, very early stage. So just want to make sure because I didn't want to give an impression that we are even in a beta testing stage. It's way earlier than that. So
even earlier. Okay. Well, let me know. I hope that I hope it can be useful in the future
sure.
for your runs.
Thanks.
Yep.
Okay, I think if there are no more questions, we can wrap up. Thank you all for joining, and we'll hopefully see you soon at another webinar or at the CMAS conference.
Looking forward to it. Thank you so much for the opportunity.
Thank you again,
Appreciate it.
Patrick. Yep.